right. We're on, we're live. Okay, so the unit circle with a radius of 1 is centered at the origin. So that means that if this is the unit circle, that is the point 1, 0. This is the point 0, 1. This is the point negative 1, 0. This is the point 0, negative 1, because it has a radius of 1 as it spins around. So we label in terms of x and y, but we also use the notation p of theta. In other words, we're kind of using function notation. Point P is a function of how many degrees the terminal arm is to get to that point. So theta is the arc length, and P of theta is defined by a point. So for example, point P here with a radius, again, if we're on the unit circle, we have a radius of 1. Then point P, again, I would maybe say P of theta, has a horizontal x component and a y component. And since the radius is 1, and since this is a right angle, sorry I drew that so ugly, Pythagoras holds, right? X squared plus y squared must equal 1 on the unit circle. What would the equation be of a circle with radius 2? Oh, no problem. It would be x squared plus y squared equals 4. Right? Because it'd just be 2 squared. So here's some important ideas when it comes to the unit circle. Point P can be defined by its coordinates, x comma y. And remember, these coordinates also, you can think of them in 2 other ways as well. You can also think of them as the triangle legs, right, that we kind of see up here, right, x and y. But more importantly, you can think of them as the cosine and sine values. Because remember, what does cosine mean again? Well, cosine, if this is theta, cosine is, of course, adjacent over hypotenuse. Well, hypotenuse is 1. So the x coordinate of a point in the unit circle is its cosine value. And sine is opposite over hypotenuse. So the y value on the unit circle for its coordinate is the sine of the angle that makes that point. And since Pythagoras is x squared plus y squared equals 1 on the unit circle, and x is cosine and y is sine, then you can say that the cosine squared of theta plus the sine squared of theta equals 1. Quick note here, this looks weird. I'm going to write, this means sine theta squared. And if you're wondering, well, then why don't you write it that way? Well, because this way I don't need a bracket, so it's less writing. But please note, if I were to write it like this, now does that mean take the angle and square it and then find the sine of that? Ah, you see there's some ambiguity there. So we don't like ambiguity in math. So if we wrote it like that, I think we would just assume, oh, if it's sine of 30 squared, if theta was 30 degrees, then I'm looking for the sine of 900. But if I write it like this, no. It's the sine of 30, which is a half, squared, and a half squared is a quarter. So there's a very big difference between these 2 numbers, right? So here, if theta equals 30 degrees, this would equal the sine of 900, and I have no idea what the sine of 900 is. What's the sine of 900? I don't know. Let's use our calculator. Let's make sure we're in degrees. 900 sine. Oh, look at that. Turns out to be 0, which I guess kind of makes sense because 180 goes into 900. And what's the sine at 180? What is the sine right here? 900 degrees would be right there. Right? Here we go. There's 180, 360. What's the next one after 360? I can't count by 18s. 18, 360, 540, 720, bit, 900. So yep, makes sense. The sine of 900 is 0 because what's the y coordinate here? 0. So the sine of 900, 0. But if I want the sine squared of theta, that's the sine of 30 squared, which is 1/2 squared, which is 1/4. So make sure you understand what that symbol means. Sine squared theta means sine of theta, figure out what it is, then square it. Okay. Cameron, you are obviously having some sort of issue with Teams. Okay. I hope you can get that sorted out. Looking at the chat there. Oh crap, and I didn't mean to say your name while I'm recording. I'll go back and try to edit that out. Example 1, a point 2/3 comma y is on the unit circle. Find the value of y. All right. Somebody at home, I'm gonna mute you there at home. Oh, you muted yourself. Okay, you're good. Oh, you're back on again. I'm going to mute you. There, you are muted. Okay, so let's do example 1 now. Example 1 says, I have a point in the unit circle, find the value of y. Well, on the unit circle, we know that x squared plus y squared has to equal 1. So if x is 2/3, and y is what I'm looking for, all I have to do is do a little bit of fractions and a little bit of arithmetic. Y squared is equal to 1 minus 2/3 squared. Okay, so how do you square a fraction? Well, you just do top times top, bottom times bottom, so that's going to be 4/9. So y squared would equal 9/9 minus 4/9, right? Because remember, when you subtract in fractions, you have to have a common denominator, and 1 is definitely 9/9. So y squared would equal 5/9. Now, careful here. Remember that when you square both sides, you have to consider the possibility that it's a plus or minus. Also, I don't know what the square root of 5 is, unless I break out my calculator and round the decimal someplace, but the square root of 9 is nice and easy to figure out. So this is the way most books would leave the answer. Simplify it when you can. Okay? And why is there a plus or a minus? Because think about it. If y is the point 2/3, so that would be, say, here's where y is 1, right? That's 0, 1. So that might be, say, there, 2/3 of the way up on the unit circle. So that could be 2/3 comma y. But isn't there another place where y is at this same height? Oh yeah, over here. That's also, oh, hang on a sec. 2/3 y, oh, hang on, I went the wrong way. Give me a mulligan on that. X is 2/3, not y. Sorry about that. Over here. There's another place where x is 2/3 of the way over. I don't know if I went, that's past a half, 2/3 of the way over. And that would definitely have a y that's negative, right? So this would be, this y would be 5/3, or sorry, root 5/3. And this y would be negative root 5/3. Okay, so it does make sense that there's plus or minus. Can't just ignore it. All right, and that's what the little note's trying to tell us. Here's an interesting question. Determine whether or not that point's on the unit circle and justify your reasoning. Okay, so basically I'm trying to figure out, does the point given satisfy the identity x squared plus y squared equals 1. This, by the way, is what we call in math a proof. So we're going to try to prove that it works. Work down when you're doing a proof, never across. So left-hand side is going to be x squared plus y squared equals 1. And I'm going to plug in, so the left-hand side, actually, I'm going to redo this. Left-hand side is going to be x squared plus y squared, and right-hand side is going to equal 1. And I'm going to make a little t-chart out of it. The left-hand side and a right-hand side. There we go. This is how you do proofs in math. So we have to prove that those two things are the same. So let's plug in the numbers. Does 2/5 squared plus 3/5 squared make 1? So let's see. Well, if I square 2/5, I get 4/25. If I square 3/5, I get 9/25. Add those together and I get 13/25. Does 13/25 equal 1? No. This does not equal 1. Therefore, the point 2/5, 3/5 is not on the unit circle. Okay? So there's example 2. Now example 3 takes us into the realm of similar triangles. Now we talked about this a little bit the other day, right? Triangles are always proportional if they're the same shape. That's what similar triangles means. And think about it logically. You've measured angles before in your life. If you have an angle and you take out a protractor and measure the angle, well, it's the same measure from there to there that it is from here to here, right? If this was 25 degrees, then that's 25 degrees. It shouldn't matter how long the lines are. The angle should be the same. And with that thinking in mind, example 3, the point P of theta lies on the intersection of the unit circle and a line joining the origin to the point 4, 3. Find the coordinates of P of theta. So let's draw a little sketch of the situation. Here's my sketch. So let's join the origin to the point 4, 3. So 1, 2, 3, 4, 1, 2, 3. So there's the point 4, 3, and there's the line joining it to the origin right there. And keep in mind, the unit circle is way back here, right? The unit circle is, of course, the circle with a radius of 1. Okay? So basically, what I want you to kind of think about, let's blow that up a bit, is in here, if I just take the part of it that goes to the unit circle, that purple triangle, which I'll just blow up here, right, that purple triangle has a radius of 1 and some y value here and some x value here. And that's really ugly. Let me fix that. But the blue triangle, that really kind of this big one, well, it has to be the exact same shape as that one. Right? It has to be the same shape, and this theta here has to be the same. But this one, I know that this height here is 3, and this base here is 4, right? Because it's the point 4, 3, right? So 4 over that way, 3 over that way. Everybody get where we're going with this? So I can call this r if you like, and I can say that x squared plus y squared equals r squared. And x was 4, y was 3. So my r here is going to be 16 plus 9. So my r squared is 25. So my r is equal to 5. But Mr. Kello, you forgot the plus or minus. Excellent observation, whoever that student was. But actually, no, I didn't. Radius never has a plus or minus sign. You can think of radius as being a scalar quantity. Those of you taking physics, you know, oh, that means it's just a number with a magnitude. It doesn't have a direction. we can't really define a direction in the coordinate system for lines that are, I was going to use the word diagonal, but you know, diagonal has a specific meaning when you're talking about coordinates. It's exactly 45 degrees or corner to corner in a rectangle or some other polygon. So I'm going to avoid the word diagonal too. The word is oblique. Oblique lines, lines that are not horizontal or vertical, don't really have a direction on the XY coordinate grid. So unlike back in the last example where it's like, oh yeah, that Y coordinate could be on the positive side of the graph or the negative side, so I think about the plus or minus. Radius, you don't think that way. You kind of can't. How do you define what direction it's going in? You could kind of maybe think about its slope being positive or negative, but in terms of its position and its distance and its length, no, it can't have a negative length. Actually, even the X and Y lines can't really have a negative length. By definition, length can't be negative, but it can have a negative length in a particular direction. But it's hard to define that direction when you're talking about a radius, because radius can be oblique. So don't worry about plus or minus when you're solving for the radius. Okay, we're not done this question yet, though, by the way, and I'm kind of lacking in room here. But anyway, hopefully you can write smaller. P of theta, we're basically ready for this now. Let me get this out of the way. I don't need that anymore. P of theta is actually, of course, now that I know that it's 5, it's actually 4/5, comma, 3/5. Can you think about why that is? Because if this line here is 5, how would I turn this line into that line? Oh, I'd divide it by 5. And it's proportional, right? It has to be the same proportion since these two triangles are similar. So if I divide this radius line by 5 to get this line, well then 3 divided by 5 will be this y, and 4 divided by 5 will be this x. Get it? That's why I know that this point here has to be the point 4/5, comma 3/5. Isn't that a nice, clever way to solve a problem like that? Okay? All right. Example 4. The point P of theta lies on the intersection of the unit circle and a line joining the point -3,6. Find the coordinates. Okay, so this time, let's make another sketch. So 3 over and 6 up. 1, 2, 3. 1, 2, 3, 4, 5, 6. Oh, that last one was terrible. Let's try to be somewhat proportional here. -3,6. There we go. So we're over there. So that's, let's make a triangle out of that. There's my terminal arm that gets me to -3, comma 6. There's my right triangle. I can kind of see it. And what do I know about this right triangle? Well, again, this right triangle, I can say that x squared plus y squared equals 1, or in this case, I'll just say r squared, right? And 6 is x. No, wait a minute. -3 squared plus 6 squared. Make sure you put that negative in a bracket, right? When you square a negative, it becomes positive. Okay, so now what kind of a number is this going to be? Well, let's see. 3 squared is 9. 6 squared is 36. So r squared is going to be 9 plus 36 is 45. Once again, I don't worry about plus or minus. R is going to equal the square root of 45. Now, careful with this one. So right now, I could say my answer is, therefore, same way we did the last one, P of theta is -3 over root 45, comma, 6 over root 45. Careful with this one. Almost every textbook would not leave the answer this way. How come? There are 2 things I can do to those radicals that would be, to most mathematicians' eyes, a simpler answer. What's one of them? Maybe I'd have even done it over here. What can you do with the number square root of 45? Do you remember this from grade 10? It's got a perfect square of 9 in it. Good. You remember this from grade, I guess grade 10 is when you did this for the first time, right? Geez, I teach grade 10. I should remember that this is in the curriculum. So 9 is in 45, and when the 9 comes out of there, that makes it 3 root 5. So a better answer might be negative 3 over 3 root 5, comma, 6 over 3 root 5. And ooh, look at that. I would never leave a fraction like that because it simplifies. So negative 1 over root 5, 2 over root 5. I would probably not leave it like that either, though. What's the other thing that you learned? This time I think more grade 11 about radical answers. We usually don't like radicals in a denominator of a fraction if we can avoid it. So this is an answer. This is a better answer. And here is the mastery level answer coming up here. We would, of course, take negative 1 over root 5 and multiply it by 1. And, of course, this is how we say 1. We would take 2 over root 5, and we would multiply it by 1, and this is the way we say 1. Right? Remember, anything divided by itself is 1, right? So I'm not changing these numbers, but I'm giving you a better answer now. This is negative root 5 over 5, comma, 2 root 5 over 5. That is the happy time, nice, excellent. Mathematicians will think that's the simplest answer. I'm not saying this was wrong or this was wrong, because they're definitely not wrong. But they're not the simplest answer. To a mathematician, 1 divided by the square root of 5 is not as simple an answer as the square root of 5 over 5. You saw this in trig too, right? Remember? The sine of 45 degrees, you always write root 2 over 2. You could write it as 1 over root 2. It's the same number. But mathematicians don't like radicals and denominators if they can avoid it. I can show you very quickly why that's true. I mean, here, think about this again. The sine of 45 degrees, you learned this in grade 11, is 1 over root 2, but mathematicians prefer seeing it that way. What if I asked you, without a calculator, to figure out what is the decimal answer there? Okay, well, if you're trying to figure out the decimal for this, and you're looking at it this way, how many root 2's go into 1? Well, root 2 is 1.414, blah, blah, blah. And how many of those divide into 1? Think about what you'd have to do. You'd have to multiply this by 10, 100, 1,000. So it'd be 14,140. I don't remember what comes after 4, so I'll just stop there. And then that, okay, so I multiplied it by 1,000, so that's 1,000. Quick. And then put the decimal there. Actually, I guess I got to put the decimal here. Quick, how many 1,414s go into 10,000? Yeah, that's a pretty ugly divide. Notice doing it this way, though. How many 2's go into 1.414? That's super easy. How many 2's go into 14? 7. Bring down a 1, 0. Bring down another 4, 7. Done. 0.707. So in the days before calculators, it really did matter that if you had to go from a fraction to a decimal, or from a rational expression to a decimal expression, you did not want radicals in your denominator ever. And so the tradition still exists that we just don't leave them that way. So most textbooks, if this was the question in your textbook, that would be the answer you'd find. So I kind of leave it to you. If you would have stopped there on a test, I'd mark that right. That's perfectly fine. I'd probably, this one here, I don't know, I might take off a mark. You should notice there's a 9 in there and a 9 in 45. Okay? But when you're doing your homework, it's kind of up to you to not, do the work, get this as an answer, and then see this in the book, and then go, oh, I'll never get it. Got the wrong answer. You gotta have a little awareness of the numbers, if you know what I mean. Okay. All right. Enough talk of radicals. Next example. Find missing circular functions when one function is given. Ooh, these are fun. I love these. Okay. Find cos and tan over the interval from 3 pi over 2 to 2 pi when sine of theta equals negative 3/5. Wow, okay. So what they're saying here is we're going to use the cast rule. Remember the cast rule? We looked at our unit circle from grade 11 the other day. Where are things positive and negative? So this is important. So on a circle, where is this? Where are you if you are between 3 pi over 2 and 2 pi? Well, this is 0. This is a half of pi, pi by 2. This is 1 pi. This is 3 pi by 2. And then, of course, back around here is 2 pi again. So my answer is in here. So basically, quadrant 1, quadrant 2, quadrant 3. I want an answer in quadrant 4. So sine of theta can be negative 3/5 in two different places. Sine is negative, cast rule. Sine is negative in both quadrants 3 and 4. But this thing's telling me we want to be in quadrant 4. That's a Q for quadrant. Okay? All right, now let's solve the problem. Now that we know where we're going, we want to be in quadrant 4. Let's draw a picture in quadrant 4. So quadrant 4, sine is negative 3/5. Oh, don't forget what sine is, right? Sine is opposite over hypotenuse. So sine is opposite over hypotenuse. But Mr. K, how did you know the negative belonged to the 3 and not the 5? Because we just talked about that. The radius can't be negative. And we know that we want to be in quadrant 4. So this line has to go down. Ha-ha! So there we go. There's my theta is here. So now I need to find the cosine and the tangent. So what's cosine again? Well, cosine's adjacent over hypotenuse, and adjacent in this case would be the x distance. So I'm going to have to find that x distance. So x squared plus negative 3 squared has to equal 5 squared. So x squared plus 9 is equal to 25. So x squared is equal to 25 minus 9 is 16. So now, okay, are we finding a radius? No, we're finding a horizontal line. So once again, I have to consider plus or minus. But look where I am on my diagram. What kind of a number does x have to be? It has to be positive. Do you see logically that it has to be positive? A negative x number would be over here. Okay, so are you cool with this? It's like, hey, wait, he forgot the plus minus. No, we didn't. There is no plus minus to be had this time. It has to be positive. X has to be positive on this side of the grid, if you want to just add that to your notes. Okay, I'm ready to solve now. If this x is 4, then the cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. And do a quick check. Remember the cast rule? Cast rule says cosine's positive in this quadrant, which it is, and tangent is negative in this quadrant, which it is. And there we go. So the 4.2 homework page has a few questions like this for you to practice, and I guarantee you one on the test. If we were doing the provincial exam, I guarantee you one of these. There's every year they had one of these. And to be honest, this should be bonus marks on a grade 12 provincial, because except for the whole positive and negative thing, this is a grade 11 question. Weren't you doing questions like this kind of in grade 11? Like, I don't know. It's just Pythagoras and SOHCAHTOA. It's not a tough problem, I don't think. Okay? This is kind of the part that's grade 12-ish right here. It's figuring out that part. Okay? All right. That, I think I'll turn the thing off here and just let you have some work time. Today's lesson was a little smaller. Come on. There we go. Okay.